Hi everyone. In this video, we're going to continue on with section 5.3, which is about rational functions, properties of rational functions rather. And in this video, we're going to focus on a horizontal asymptote of a rational function. Right? And the horizontal asymptote of a rational function is a little bit trickier to sort of tease out than a vertical asymptote. With a vertical asymptote, all we needed to do was simplify the function and find where the denominator equals 0. Okay? And that gave us our vertical asymptote. There's a bit more nuance when we're talking about a horizontal asymptote of a function. To do that, what we need to do is to look at the behavior of the function as x approaches infinity or maybe negative infinity. Okay, but it turns out for what we're doing now, we're going to generally focus on positive infinity. Okay, and so what we're going to need to do is not really decompose, but we're going to need to look at the top and the bottom of our rational function very closely. And we're going to need to pay special attention to the leading terms or the highest monomial in our polynomial. Okay, so we need to look at the leading coefficient and the leading exponent, because that's what's going to help us determine what type of horizontal asymptote we have. And actually, we're going to be introduced to another type of asymptote called an oblique asymptote. And we'll see what that is in just a second. So, once I look at my rational function, which I'm going to call R here, and I find the leading coefficients, I'm sorry, this should be B here. That's my bad. Okay, so B with a subscript of M. And then the actual exponents on the leading term, on the leading monomial. We need to look at them, and based on the numbers, based on the coefficients out in front and on the exponents, it determines what type of horizontal asymptote we have. So, if n is less than m, meaning that the highest exponent, the largest exponent on the top, so the largest exponent for p of x is less than the largest exponent for q of x, then y equals 0 is going to be the horizontal asymptote. So the horizontal asymptote would be the x-axis. Okay, if the power on top, the largest power on top is less than the largest power on the bottom. If the two are equal, then we use the leading coefficients, A and B, to determine the horizontal asymptote, and it becomes A divided by B. If n is equal to m plus 1, meaning that n is 1 larger than m, then the function has an oblique asymptote. We'll see again what that oblique asymptote looks like. Okay? And if n is 2 or more greater than m, then there are no horizontal or oblique asymptotes. Okay? There are going to be no horizontal or oblique asymptotes. So, we have a number of different things that we need to consider here. So, let's look at some examples. So, if I look at the first, I'll label this as always 1 and 2. If I look at number 1, I want to see I want to see the monomial that has the largest exponent in the top and in the bottom. And so, as I've arranged it in a nice way, it is 4x cubed and 7x to the 5th. So that means A is 4, b is 7, n is 3, and m is 5, if we follow the sort of definition that we laid out before. And because n is less than m, then the horizontal asymptote for this function is going to happen at y equals 0. It's going to happen at the x-axis because n is less than m. Okay? Oh, sorry about that. My pencil's about to die. Okay, so that is that first case. Now, second case, for f in number 2, the leading term is 3x to the 4th on the top and x cubed on the bottom. So again, if I labeled everything, a would be 3, b would be 1, n is 4, and m is 3. Since n is equal to m plus 1, meaning that n is 1 greater than m, so x to the 4th is 1 greater than x to the 3rd in terms of exponent, then the function has an oblique asymptote. An oblique asymptote. And what an oblique asymptote looks like is in the bottom here. Okay, in the bottom. So the function is in blue, and then the oblique asymptote is in sort of purple dotted. I know it's not a very large picture. Maybe I can, zoom in here more. We aren't actually in this class going to discuss how you would actually find this oblique asymptote. But I guess if you wanted to, it's really not that hard to understand. The slope of the oblique asymptote is a divided by b, so that's why it's 3x, okay? And then the plus 3, it comes from something a little bit more complicated that we just aren't going to bother with in this class, okay? But if n is equal to m plus 1, then there is an oblique asymptote. So what I would want you to write on an exam or anywhere else in terms of this class is, there is an oblique asymptote. All right, that's all I want you to write for now. We may discuss in class how to find what the oblique asymptote is, but we'll determine that at a later date. Okay, so your turn for this section. All right, I have two functions here. I want you to define or find the horizontal asymptote or oblique asymptote for each of these functions.